For nearly 30 years, physicists have solved the mystery of cosmic acceleration the same way. Take Einstein's equations. Notice they don't predict the acceleration we actually observe and manually insert an extra term to make the numbers work. That term is dark energy. Nobody knows what it actually is. It was added because the math demanded something, not because anyone detected it directly. In October 2025, a team of physicists asked a very different question. What if the problem was never a missing ingredient at all? What if we've simply been measuring the universe with the wrong shape of ruler? To understand what that means, you need a quick picture of the geometry Einstein's equations actually rely on. Standard general relativity assumes that the distance between 2 points in space is the same no matter which direction you're measuring it from, a smooth, evenly curved geometry called Riemannian geometry. It's the same assumption baked into most of the physics you learned in school. But there's a broader, more flexible kind of geometry called Finsler geometry, where distance is allowed to depend on direction as well as position, useful for describing things like gases, where particles are genuinely moving through space in every possible direction at once, each one experiencing the geometry slightly differently. A team led by physicist Christian Pfeifer at the University of Bremen, working with mathematicians at the Transylvania University of Brasov, decided to rebuild the equations describing the universe's expansion using this more flexible Finsler geometry instead of the standard version. And what came out the other side genuinely surprised them. The resulting equations, which the team named the Finsler-Friedmann equations, naturally predict an accelerating, exponentially expanding universe, even in a completely empty vacuum with nothing added by hand. No dark energy term inserted to force the math to fit. No extra unexplained ingredient assumed into existence. The acceleration simply falls out of the geometry itself, the same way gravity falls out of curved space-time in ordinary general relativity. Pfeifer described the implication carefully. This is an exciting indication, he said, that we may be able to explain the universe's accelerated expansion, at least in part, without dark energy, based purely on a more general description of space-time geometry. Not a definitive answer, an indication. A genuinely new door opening in a debate that has been stuck behind the same door for 3 decades. Here's why this matters beyond the specific equations. This is now the second serious geometric alternative to dark energy this channel has covered, and the 2 proposals attack the problem in completely different ways. The timescape model we looked at previously argues time itself passes differently across dense and empty regions of the universe, creating an illusion of acceleration. This new Finsler approach argues something more fundamental still, that the very shape of space-time, the geometry Einstein built his entire theory on, might simply be more flexible and direction-dependent than assumed from the very beginning. Different mechanisms, different mathematics, but both converging on the same underlying suspicion that dark energy may be less a discovery and more a patch, covering a gap in a geometry that was never quite complete. Now, the honest caveats matter here as much as the excitement. This is an extremely new result, published in October 2025 and still being tested and scrutinized as we head through 2026. Pfeifer himself is careful to say the acceleration may only be explained, at least in parts, by this approach, not entirely, and the model has not yet been checked against the full weight of observational data the way the standard model has been tested for 30 years. It is one promising direction among several competing ideas currently being explored, not a finished replacement for dark energy. What is genuinely encouraging is the direction all of this research keeps moving in. Rather than continuing to add unexplained ingredients to make old equations fit new data, physicists across multiple independent teams are now asking whether the equations themselves, the very geometry underlying our description of the universe, might have been incomplete from the start. Whether that turns out to be time behaving differently across the void, or space itself curving in ways ordinary geometry can't capture. Either answer would represent one of the most significant shifts in cosmology in a generation. What do you think? Is the acceleration of the universe hiding in an unexplained substance or hiding in a mathematical shape we simply hadn't tried yet? Let me know in the comments. Subscribe, because next time we are finally covering quark stars, a theoretical object even denser and stranger than a neutron star, made of matter crushed so violently that neutrons themselves are believed to break apart entirely.